Today's lesson isn't going to be in reference to the inclined plane. And I do have an image here to help you visualize what we'll be talking about. An inclined plane, usually referred to as a ramp, is referred to as an inclined plane. Just want to make sure my mic is working. Yeah, it is. It's referred to as an inclined plane since any flat surface is referred to as a plane, planar. And to incline something means to just raise it up to a certain angle, called an inclination or incline. So we refer to the everyday ramp in physics as the inclined plane. And the general goal of the lesson and one of the learning objectives for students when learning this topic is to be able, or the first one would be to be able to understand how forces of gravity, gravitational forces, Earth's gravitational forces play out in terms of the direction of the forces acting upon the block. And this is be a block here sitting on top of the ramp, about to slide down the ramp due to gravity, Earth's gravity. And students need to know exactly the details of how weight, the object's weight, which we call the force of gravity, how the mathematics is used to model the amount of force that pulls something down the ramp. Well, or you could say, how do you mathematically model how much force from Earth's gravity pulls the block directly into the ramp with a force that's perpendicular to the surface of the ramp? Or how does the ramp respond to that by pressing back up in a direction perpendicular to the surface of the ramp, pushing back up on the block? Those are all forces that are important to understand in the topic of the frictionless incline, which is always the starting point, to establish students' understanding of these things I've just discussed, and then move into a more extended conversation that would include friction. So the real ramp, of course, most things go sliding down ramps don't experience zero friction, but some frictional effect in most cases would occur. And so we then have to extend today's discussion into another lesson, which is similar but different because it will have to include friction. But today, and for right now, my goal is to have you better understand this image, which is an important image, in my opinion, for students to not only conceptually understand the physics involved with inclined planes, but to be able to do some of the math relating to some of the word problems that you would typically see, especially on AP exams. All right, so let's begin. I'm going to expand my writing screen, just see if my camera can zoom, or not zoom, but focus in on my pen. Sometimes it takes a moment for the focus. There it goes. Okay. So what I'm going to do is let's draw it in this direction, straight down. This is my inclined plane. Oops, sorry, not a great. Maybe I'll use this instead. This is my inclined plane drawing. And the ramp. And what we usually say is that the ramp, which may, could even be just a plank of wood, which usually would start flat. It was just a plank of wood laying on the floor, that you would raise the plank of wood up and then rest it maybe on something that's like a corner of a table, right? And so that angle that you're raising this plank of wood up to is referenced here. And that's usually called the angle of inclination. It's just known as you think of it as the angle of the ramp angle. And usually what these problems are, the way they're depicted in physics, introductory physics classes, is that there's a box or some sort of box-shaped object that is at rest on the top of the ramp. Maybe you're holding it with your hand, and then you're going to just release it. And then it's going to slide down this ramp. Ultimately, when you watch something slide down a ramp or go sledding down a hill, you'd have to think, well, what force is causing that motion down the hill? And of course, we know that gravity causes things to fall with an acceleration, right? If you dropped a ball, we know that in equal amounts of time, if this was 0.1 seconds of, this is the 0-second mark, this is where the ball is. And then here it's at 0.2 seconds, and then here at 0.3 seconds. In equal intervals of time, which in this case is in tenth of a second intervals, we see that it increases the distance it travels in that interval of time. That each displacement in that interval is always a larger in amount than the displacement in the previous equal interval of time, which is larger than the previous distance it achieved or displacement achieved in that same interval of time, because they're all separated by 0.1 seconds of time. And we already established that that's the motion map for accelerated motion, because it's a good visual that helps you provide a visual model or way of thinking about how something moves when it's accelerating. It always has this kind of pattern, right? Of course, that's different than constant speed motion, which if this object were falling at a constant speed, these would all be equally distant. The 0.2 second mark would have been here, 0.3 second mark would have been here, and they would have all been equal distant. And that would have been a model for constant speed motion, because if you're going at a constant speed, you move equal amounts of distance in equal amounts of time. But not when you're accelerating, right? It's always extra distance covered in every additional interval of time that you're given to move compared to the previous interval of time. It turns out that that's still true for acceleration, which I don't mind. I did this in the other class, but I'll do it now. It only takes me a second. Let's just type in pivot interactives. Just bear with me here. So this gives a good visual that I'm about to show you on this website of what I'm talking about. Let's see if we type in ramp. Here's 124. Okay, so let's take a look at this here. Right. So we have ourselves a ramp, as I've described, propped up with something. And this is technically the ramp angle right here. I don't know what it is, but 20 degrees, 25 degrees, I'm not sure. It's not important. The important part right now that I'm trying to have you visualize is this idea that I just described, that in equal amounts of time, equal intervals of time, this block will move greater distances compared to the previous interval of time in terms of the distance it had traveled in that previous interval of time. And that pattern should continue, and that would be a way of identifying accelerated motion, right? And so we have our stopwatch here. I can forward in this video to locate the spot where the string, you'll notice the string is holding it up right now, but I'm going to cut it. Right about, oop, there, he just cut it. Back up a couple frames just to make sure. One more frame forward, boom, right there. So now I would zero my watch, my stopwatch, because I need my stopwatch to keep track of these intervals of time. And I could just, mark this up with, using the center of the block in this case to mark the position of this pop. This is actually a frozen dry ice, CO2. So it's moving more or less with no friction down this very smooth ramp. Some friction, of course, but very small amount. So the point is that now I can forward, since I've zeroed my stopwatch, some amount of time. I'm going to choose 0.2 seconds. Back up a little bit. There it is. You'll see the time value right here, 0.2 seconds. And now I can mark it right in the center just to get a visual on the distance it travels every 0.2 seconds. That's what I'm doing here. Let's go forward now to the 0.4 seconds. That was the 0.2 second mark. Let's go to 0.4 seconds. It's right there. And you'll see that the pattern that I previously described with a free object in free fall, which is falling straight down, only due to the force of gravity and no other forces, no air resistance. That's the criteria for free fall. But I had shown the pattern that unfolds as something falls straight down. You'll notice that the same pattern starts to unfold, because now I'm going to the 0.6 second mark. We went 0.2, 0.4, now it's 0.6 seconds. You see that it's the same pattern, right? This is evidence that something is accelerating, because in every interval of time, in this case, every 0.2 seconds, the distance it travels is larger than it traveled in the previous interval of time, which is larger in distance than it traveled in the previous same interval of time, right? So this is the concept behind acceleration. When we know, that's one of the bases for this entire conversation, because we're going to be talking about Newton's laws of motion, and Newton's laws can be used to describe how forces, unbalanced forces most specifically, cause accelerations. And the idea that the rate of acceleration, how rapidly something gains speed, depends on how much unbalanced force there is, called the net force. It also depends on the mass or inertia of the object. More mass or more inertia reduces the object's acceleration, while more force, more net force, I should say, more unbalanced force would increase the acceleration rate of the object, right? Generally speaking, that's just a qualitative description of Newton's second law. But we're going to be tackling it more quantitatively now. So now, let me go back over to here. Let's talk about forces, because now you've seen that what I just showed was, before I guess we talk about the forces, just that the idea that this thing moves down the incline greater and greater distances, speeding up faster and faster. That was the ramp. And this was the block. I guess it's hard to see since I made those little wavy lines just to show that it was moving. This is acceleration. This is the motion map for acceleration. The distance is increasing for each interval of time. I'm not going to write that all out, but that's the idea. So now let's talk about the forces that cause this effect, right? Because according to Isaac Newton, there must be some unbalanced amount of force on the block that causes this object's speed to increase as it goes down the ramp. So let's tackle that. Very important question. Let's just start with, what are the forces, right? We know that there's a downward force of gravity. This is usually written Fg, the force of gravity. I can put the magnitude symbol there if we want, which is, by the way, just the weight of the box. Pulls straight down, even though it can't move straight down. Earth's gravitational pull is always in the downward direction, regardless of your direction of motion. And now what's important, before I go into what's called the components, is to describe this little trick that teachers have used, which is to take your normal absolute XY axis, which is the one you're used to, which looks like this. And we're going to turn it. This x-axis that usually goes this way, we're going to turn that x-axis so that the x-axis actually goes straight down the incline like this, so that all of the motion of the block is now in the x direction. Because otherwise, if we stayed with our absolute axes like this, x and y, then as this thing moves down in this direction, down the incline, it technically will be moving horizontally as it goes along this line, but it will also be moving downward vertically as it goes like this, right? And then we'd have to deal with two components of motion. So this adjustment that we're going to make now, which is to skew these axes and turn them, allows us to, which I'll put right here, x, y is now like this, allows us to say that the motion of the block is only along this axis, along the x-axis. This is called a skewed axis. And that's what you want to do. For always, when you're doing these physics problems, it makes life a little easier, so you want to do that. So now that we've done that, right, now that we have an x and a y axis like this, what we have to do is resolve this vector into its components, which means technically if this is our xy axis, I should be able to draw in an x component that goes parallel to the x-axis. And I should also be able to draw in a vertical component right here. I shouldn't say vertical because vertical really is up and down, but I should be able to draw I should say y component, because this y component I can draw in a moment will be parallel to the y-axis, right? So yeah, this is going to involve some geometry, some trigonometry. So let's do that. This one right here goes down. Notice that that component that I just drew is parallel to the y-axis. And then the x component to this gravity force goes this way. And notice that that component is parallel to the x-axis, right? So for those reasons, we call this the x component, FGX, for the x component of the gravitational force. And then we refer to this as the y component, remembering again that the x-axis goes side to side. I'm just going to draw it here, but maybe I don't want it to mess up another vector. I'm going to draw a little bit. The other thing to know is that once you've created this vector triangle, which is an important part of learning how to model and understand the original image I showed back in the beginning of this video, is that this angle right here, this ramp angle, is the same as this angle right here. This angle. Those angles are the same. And there is a theorem in geometry that proves that that's true. Because with two triangles that are similar triangles, if two out of their three segments are parallel, then they must be similar triangles, and therefore they have the same interior angles. So if I look at this as triangle 1, this big one, and this is triangle 2, as long as I can find that 2 out of the 3 segments are parallel, let's see, this one is parallel to this one, and then this one is parallel to this one. Well, that's it. That's 2 out of 3. These must be similar triangles, which means the interior angles must be the same. The more convincing method is just to make this with paper. Cut this piece out of the paper, flip it over and rotate it, and it would snug right into here, nice and neat, proving to you that that original angle fits right here, and therefore it must be the same angle. But once you buy into this idea that that angle is the same, we can then move forward with modeling this amount of force, FGX or FGY or FG, with some trigonometry. That's what we'll do now. So let me draw this a little larger. Like this. Oops, sorry. Sorry. Just got hit. There you go. So what I'm going to do is I'm going to draw this triangle, this vector triangle, a little larger so we can look at it a little more closely. So what we know is that this vector right here is the gravitational force vector, and known as the weight, right? The weight of the object, which is equal in magnitude, right, to the product of mass and the acceleration due to Earth's gravity, or any planet's gravity. What you weigh on a planet is equal to the gravitational acceleration due to gravity on that planet, which varies from planet to planet. It's only 9.8 here on Earth, multiplied by the mass, right? So we know if someone said, how long is this? It's mg long. I don't know what it is numerically. You'd have to know what the mass is and multiply by 9.8, but we're just referencing things in terms of variables right now, symbolically referencing these things. You want to call it that. This, on the other hand, remember, is the y component. This right here is the y component, fgy, right? And this one was fgx. Now you might first ask, what do these components effectively do? What effect do they have on the motion of this? Well, we knew that the object had moved down the ramp. I'm not sure why my light won't brighten anymore. A second, sorry. Huh. Totally. The wire's touching. Sorry. So we knew that the block would slide down the ramp, and we saw that. I proved that, and we saw that this was the pattern, right? Why was it moving? Well, something only moves in a certain direction, like it had here, if there was an unbalanced force in that direction. There must be some amount of force pulling it down the hill, right? Who is that force? You see that it's fgx. The x component of the weight force is effectively pulling that object down the ramp. So it's worth noting that fgx pulls the object down the ramp. And fgy, what does fgy do? Well, you can see it's providing a force in this direction. So if you were pressing down like this on this block, pressing down, it would essentially press the object into the surface. It causes some pressure under here, right? Harder amount of pushing in this direction would cause more pressure in here, right? So it essentially squeezes the object against the surface that it rests on, right? That's what fgy does. It pulls the object directly into the ramp. You might say it's perpendicular to the ramp surface, in the sense that the ramp surface goes this way, and this force we're talking about, fgy right here, is perpendicular, right? This would be a right angle right here. Okay, that's what they effectively do. One presses it or pulls it directly into the ramp. The other actually pulls it down the ramp. How would we figure out how much that force is? What amount of force is that? Well, we get to use a little trig, right? Because we know that we want to model fgx and fgy using some math and some trigonometry. Well, we would see that fgx is opposite of the angle that we're talking about, right? And which one goes with opposite out of our trig function? Sine, cosine, or, well, I just say sine or cosine. It would be sine, right? Because you might remember that the sine of an angle is opposite over hypotenuse, right? So the sine function goes with opposite out of the two, out of sine and cosine. Tangent does also, but it's not what we're interested in, because we need to relate it back, our function back to the hypotenuse, which is mg, because we know that value. And the hypotenuse is not in a tangent function. That's opposite over adjacent. But a hypotenuse does appear in the sine, and of course it does appear in the cosine function. But the one that involves the opposite, which we're pointing out fgx is opposite, would be a sine function, right? And so just remember, in general, like we've talked about in the past, if we said, this was our xy axis in general, and this was vector A, that this has components as well. This is what we call AY, and this is what we call AX. And AX would be the magnitude of A, the hypotenuse. AX would be, on the other hand, adjacent adjacent to this angle, because this AX is adjacent, so it would be cosine theta. And AY would be magnitude of A sine theta. Notice that there's going to be something slightly different in this case, because we're drawing the angle as going to the vertical, right? So this is one of those exceptions where the X component usually goes with cosine and Y component usually goes with sine, but in this case it won't. All I was really trying, so be aware of that, but all I was really trying to point out is that the general format for a component, of course, is the hypotenuse times either sine or cosine of that angle, right? So what is our hypotenuse? Our hypotenuse is magnitude of FG, or weight, the full amount of weight the object has in newtons. Oh, sorry, I was pointing to this one, and maybe it was making a mistake. FGX is this one. So FGX will be, like I said, the full weight, the hypotenuse. This is now opposite, so that opposite goes with sine, so I would write sine of the angle. And all I have to do is recognize that weight, we know, is mg, right? So the amount of force that pulls the object down the ramp is equal to mg sine theta. We don't know what it is. We just know that it's going to be some percentage of the weight, right? Because a sine function, remember, is a percentage, right? A sine function varies from 0 up to 1. 0 is like 0%, and 1 would be 100%. It's always a decimal for all of the angles in between 0 degrees and 90 degrees, which this would be in between 0 and 90 degrees, right? This will be some angle here, certainly between 0 and 90 degrees. So in a lot of physics, when you see the sign, you think of that as a percentage. And this, remember, is the weight. So it means that the amount of force that actually pulls you down the ramp is some percentage of your weight. So for me, if it was, I weigh 800 newtons, and if this percentage came out as when I put in sine of, I don't know, let's just say it was sine of 30 degrees, let's just say, sine of 30 is technically 0.5, which is like 50%. That means if I slide down this hill with my sled, assuming there's no friction, actually it doesn't even matter if there was friction or not, it's still true that friction or not, if I slide down this hill on a sled, the amount of force pulling me down in that direction, causing the motion, would be 50% of my weight. Again, if it was sine 30, because this angle was 30 degrees. My weight was 800 newtons, then it would be 400 newtons of force pulling me down in that direction. So this is an important part of the step that we have to follow if we're trying to figure out what is the rate that the acceleration rate, the rate that the speed increases, called acceleration, right? Delta V over delta T. What is that rate? You've seen that we can determine the acceleration rates from kinematics by measuring distances and times, and we've done that in the Pivot Interactives labs. But you can also predict and that way I just described is more of an experimental approach, watching a video in slow motion and measuring distances and time, and you're making direct measurements for distances like these and the time it takes to determine the acceleration. That's more of an experimental approach. This method is more theoretical, meaning we don't have to make direct measurements. We can actually predict what the acceleration would be if there was no friction on a ramp that has some angle, using Newton's laws without having to reference kinematic equations at all, without having to reference time at all, just based on Newton's laws of motion. Because remember, his law is that the acceleration is equal to the net force divided by the mass. Or other times it's written the sum of the forces in the x direction divided by the mass. And we're talking about x direction because remember, this is our x-axis now. It's our x-axis. So we can calculate, again, acceleration without having to measure distances or time. We just need to work out, again, this isn't a direct measurement. This is an experiment. This is not experimental. This is just a prediction. But as long as we know what the unbalanced amount of force is and the mass of the object, we should be able to predict the acceleration. So let's go back to our drawing to talk about the net force. We see that this weight has broken into two components. So we can imagine that this one's not there anymore. And it's effectively acting as two different forces, one in this direction and one in this direction. If gravity is pulling on this block down into the surface with this amount of force, what will the ramp do? Well, let's just think about standing on a floor, right? If you're standing on a floor with your feet, this is your feet, your shoe, we know that the total amount of your weight is pulling you down in amount of mg, right? It's your weight. And therefore, Newton's third law says, since the earth is pulling you into the floor will respond with an equal amount of force, also equal to mg, but opposite in direction, an equal and opposite reaction. A reaction has an equal and opposite reaction. That's what that means. And we call that force the normal force, right? So the normal force, which is perpendicular to this surface, it's always perpendicular to the surface, will be equal in amount to however hard it's being pressed in or pulled in. Gravity technically pulls. Well, we can say that same thing over here because we're talking about forces and we're trying to figure out what is the unbalanced amount of force. Well, we have to include all of the forces, right? Because a free body diagram, if I were to do one, would have included Fg, free body diagram for this block. And we know that the normal force always is perpendicular to the surface. So that would technically be in this direction, right? This direction. Yep. And if there was some friction, which there isn't right now, because we're not talking about friction, if it's moving down this way, the friction would be up the ramp, and I would draw that here heading up. Might be a small amount, so it might be a smaller vector. But right now, this is a frictionless ramp. Those are our forces, right? And we've again taken the gravity force and broken it into two components. And now we have to represent the normal force. The ramp's reaction to feeling it, the block being pulled into it, the ramp reacts by pushing back up in the same direction with an equal amount of force, right? This amount of force is equal to this amount of force. And they have to cancel. Those have to be balanced and cancel because it's not going to move in this direction. That means this one would have to be longer. It's not going to move in this direction. That means this one have to be longer. It's moving in neither direction. It's moving perpendicular to those two vectors, right? It's moving in this direction, which means these have to be balanced and cancel, right? And so in this discussion now about the net force, which is essential discussion to have if you're trying to figure out what the acceleration rate is. Then again, what we would do is realize that the normal force, gravity force like this one goes down, this is our FGY, and this is, that wasn't very well drawn, sorry. This is FGX, right? So these cancel. These are balanced, right? Those are balanced forces because they cancel. If this amount of force right here is 30 newtons, then this amount of force in the upward direction from the ramp is also 30 newtons, and they would cancel. Two forces that are in opposite direction but equal in magnitude will cancel and be called balanced forces. Which is the only one that's unbalanced? Again, since we resolved this already into these two vectors, this goes away. So out of these three pieces, where's the unbalanced amount? Right there. This is unbalanced. These are balanced. This is unbalanced, right? What do we call the unbalanced force? The net force. In our diagram, was there an equation for this? Yeah, we called it FGX. Do we have a formula for FGX? Yep, we did some trig and worked out that FGX is mg sine theta. So what does this mean? It means that we can now, when we use Newton's second law to work out the acceleration as it slides down this ramp, we can pluck away the net force in the x direction, which remember that is our x-axis, and simply place FGX, because FGX is unbalanced. And then you're like, well, pluck that away also because we have an expression for FGX, mg sine theta, right? So that's where we're at right now. Let me grab another piece of paper for that. So since we have A is equal to the net force divided by the mass, the acceleration of the block down the ramp is proportional to the net force and inversely proportional to the mass. We can say that the net force is FGX, and FGX is mg sine theta, based on what I've just described. Again, it's abstract, perhaps, because it's just represented with variables, but it can become numerical to represent a true amount of force pulling you down the ramp. Again, if mg for me, I'm about 80 kilograms, g is about 10, so my weight is actually 80 times 10, which is about 800 newtons. And if it was a 30-degree ramp, as I talked about before, sine of 30 would be a half, and a half of 800 would be 400 newtons. Sliding down a hill, how much force is pulling you down that hill? 400 newtons. Mg sine theta is the amount. But it varies because it depends on the mass of the object and the angle of the ramp. So we have to represent it with variables so that we can apply that to any scenario for any person or any object with any mass and any ramp with any ramp angle. Divided by the mass, notice that the masses cancel. This is math's indication that if the object is accelerating down a frictionless ramp, that the mass of the object that's sliding down the ramp will not matter. It's claiming that if there was, for example, a ramp, you had one ramp like this, and another similar ramp with the same angle with a much heavier object on it, but they had the same angles, and both were frictionless, and you release them because they're both starting at the same spot, that they would go down this ramp at the same rate. They'd be side by side, they'd gain speed at the same rate. Their acceleration would not depend on their mass. What we say is it would be independent of mass. And the indication there is that the mass cancels. And we know that's true for, dropping these two. If I drop this one and drop this one, right? When this one's here, this one will be here. When this one is here, this one would be here. We already know that two objects that are solid objects, at least, that don't have a massive effect from air resistance due to like their light mass, like a feather, two solid objects, even if they have very different masses, will accelerate at the same rate, right? Turns out that this is saying same will be true. They'll accelerate at the same rate regardless of their mass. And so we get a little squiggly here. I might as well make the most of the squiggly. What we get is that the acceleration formula is g sine theta. Remembering that sine theta is really a percentage, since it varies between 0 and 1, right? If I were to plug in let's clear this, sine of 0, I get 0, right? Just reminding you. Sine of 0 equals 0. Oops, I didn't mean to put theta there. It's supposed to be a 0. Sine of 0 equals 0. How about sine of 30? A half. How about your typical angle? Sine of 45. 1 over root 2. 0.707. How about sine of 60? 0.86. What is this number approaching? Sine of 90? 1, right? That's why we can think of a sine function where the angle varies from 0 degrees up to 90 degrees, always as a decimal between 0 and 1, and therefore, why not think of it as a percentage, right? 50%, 71%, 86%. So it means that our acceleration as we accelerate down this hill will always be some percentage of g. It will not be g. The only way that you can have it be g is if you take this ramp angle and turn it all the way up like this, so that now the block is actually sliding straight down, and now all of its weight is in the direction of motion. Notice that that's not true here. All of its, does not represent all of its weight. This represents all of its weight. So something less than all of its weight is in the direction of motion, which means the acceleration will be less than 9.8. But if you, again, take this up to 90 degrees and now it goes into free fall, well, as we said, you can put sine of 90 there. What would you get? 1. So that means when sine of 90 is 1, your acceleration in the downward direction in free fall is g. But whenever you have some ramp effect, some angled effect because you're going down a ramp, the acceleration will always be less than g. Super important to just conceptually understand that. Acceleration down a ramp will always be less. Acceleration down a ramp will always be less than g. Acceleration is only g when falling straight down in free fall. Which means there's no air resistance either. If there is some air resistance in the upward direction as you're falling down, then that will reduce the amount of net force from being your weight, if it was just your weight pulling you down. And now if there's an upward amount of force from air resistance, like my weight was 800 newtons, right? My example. But if there's 100 newtons in the upward direction of air resistance because my body's falling down, let's say because I'm skydiving, now the net force isn't 800, it's now 800 minus 100 in terms of magnitude, which means the magnitude of the net force for me is not 800 newtons my weight anymore, it's now 700 newtons. And since the net force is something less than my weight, the acceleration would be, again, something less than g. So you only accelerate at a rate of g when the net force is equal to what you weigh. If there's any effect that's causing the net force to be less, it can be the inclined plane example that we just discussed, or it could be due to air resistance, falling straight down, but air resistance, which reduces the net force, then your acceleration will always be less than g. If, on the other hand, the net force is equal to twice your weight, by the way, this is just extra, not relating to this, but if the net force on you, as someone pushes you, is equal to 2 times what you weigh, if the net force on you is equal to 2 times what you weigh, this is your weight, then you will accelerate at 2g, approximately 20 meters per second squared. So on Earth, again, if I weigh 200 pounds, so if you pushed on me sideways so that there was a net force of 400 pounds on me, I'd accelerate at that rate. After 1 second, my speed would be 20 meters per second. After 2 seconds, it would be 40 meters per second. Accelerate at 2 Gs. If the net force on me is 3 times my weight, same effect, my acceleration is 3 Gs. 5 times my weight in terms of the net force, that's 200 pounds. That means you have to push on me with 1,000 pounds of force. I would accelerate at a rate of 5 Gs. Just a little extra there. Knowing just that in this conversation, again, this is not an effect that causes accelerations more than g. These are all the effects that I'm talking about here that create accelerations less than g. Okay, and this is useful because, and in this last example, someone said, what is the acceleration mass m down a 30-degree ramp. What is the acceleration? And I should say frictionless ramp, because this is only for when there's no friction. This only works for the no friction case. We will be tackling the friction case relatively soon. No friction. Oh, you would just use that. You'd say G is 9.8. Sine of 30, because they're saying it's a 30-degree ramp, which again is 0.5. So you will accelerate at 4.9 meters per second squared. Right? And then you could have a kinematics problem. And sometimes it leads directly into that. You know? How long does it take for this thing to slide from here to here? Well, in kinematics, you can answer those questions as long as you know the acceleration rate. How you get it? That's how you get it. Now, if someone tells you the length of this, for example, how long does it take to reach the bottom of the incline? Now you're back to kinematics equations. You've got the acceleration numerical value, and now you're back to unit 1. Right? All right, that ends it for me. I will be providing another lesson, which is an extension on this, part 2, which involves similar things, but involves friction as well. All right, hope that was helpful. Seeing you soon.